me!
That's what I'm talking about.
Wait!
Okay, now, from the beginning.
Welcome to day 2 of the virtual events for launching the PPI Center, where we continue to ask the question, how do you turn adversity into opportunity? I'm so excited to introduce our co-host here, Shiv Mishra, who is the co-director of the Colorado site. Shiv, can you tell our participants what they're going to experience today?
Hello, everyone. We are so grateful that you have taken the time from your busy schedule to attend today's events. As Danny mentioned, I am one of the 2 co-site directors of the Colorado site, along with Professor Evan Chang. And we have a very exciting and intellectually stimulating agenda planned for you today.
Wow, so both exciting and intellectually stimulating. That's the killer combination. What's going to happen today, Shiv?
Yeah, so we will start off with 6 very exciting project presentations from the faculty from Oregon State University and University of Colorado Boulder. The topics that we will be covering today will include machine learning, visual analytics, reinforcement learning. Feel free to use the chat window to post your questions and comments as you listen to these presentations. We'll follow this up with a session called Ask Me Anything, where you'll have the opportunity to ask any clarifying questions from the 6 presenters. And at the end of that sessions, Dr. Dee Hoffman will give a presentation. She's our NSF evaluator for this center.
Wait, this is the Dr. Dee Hoffman.
Absolutely, this is the doctor. Yeah, this is the D Dr. Dee Hoffman.
Okay.
And finally, we'll have 2 rounds of small breakout room group discussion sessions.
Wait. I thought it is unsafe to be in the same room with other people.
Oh, don't worry. We are using Hop-in platform. Where we'll have a separate virtual breakout room for each presenter, where the presenter can provide more details about the project. He or she will seek suggestions from you and essentially chart a course where we can take this project forward with your collaboration.
So you said it's going to be exciting. What happens if I don't find excitement? I went into a room and I don't find excitement in that room.
Oh, don't worry about it. Hop-in allows you to basically leave a room anytime and move on to another room. So you have the opportunity anytime to simply leave the room and go to a different room.
Remember, so I can hop in on hop-in?
Absolutely. You can hop in from one virtual breakout room to another breakout room anytime.
Oh, that's cool. Now that's what I call exciting.
So we'll end today's sessions with several options for you. You can do another round of speed networking to meet and greet other participants. You can enter an expo booth called the Yes Desk, where you can ask any questions about the center, or more interestingly, you will hear the nice music that Danny will be playing on his guitar. And finally, you'll have the opportunity to enter the D booth, where the Dr. Dee Hoffman will answer any questions you may have about the written feedback that you will provide for the project proposals. So let's get started with the faculty presentations now.
This project is on open set detection, and it is joint work with my colleague Minsuk and my PhD student Matt Olson. Machine learning classifiers are everywhere in the world of IoT. These classifiers classify data instances as belonging to one of k possible classes that it saw during training. Here are 3 examples. In smart agriculture systems, there's an interest in classifying plant images. For instance, you might want to classify them as crops or weeds so that you can decide what to spray and what not to spray. In network security, there's an interest in IoT device classification based on the network traffic that they generate. And finally, in smart homes, there's an interest in classifying appliances based on their load profiles. One of the major issues with machine learning classifiers when they are deployed in the real world is what happens if it encounters data from a class that it did not see during training. For example, in my smart agriculture application example, it might encounter poison oak, and it's not quite sure what the classifier will do. For instance, a classifier may classify it as basil, it might classify it as mint. We're really not sure, and it's quite unsettling because it's so unpredictable. A solution to this problem is an area of machine learning known as open set detection. In open set detection, the goal is to detect novel classes seen during deployment that were not seen during training. And of course, you still want to maintain high accuracy on the classes that were seen during training. The long-term objective of open set detection is to improve robustness of real-world machine learning deployments to these unknown unknowns that they encounter. Another objective is to improve user trust in machine learning systems. For example, I know that I, as a user, would feel a lot more comfortable if that smart ag system said, hey, here's something that is the poison oak that I've never seen before, and it alerted me to this particular unknown instance. For year one objectives, the goal is to identify weaknesses with state-of-the-art approaches in open set detection, and we would also like to develop new and improved open set detection algorithms based on density ratio estimation. Here are more details. The majority of algorithms in open set detection rely on cross-entropy loss to do the training. My lab has found that this loss tends to produce some pathological behavior in some cases, and we would like to understand this a little bit better. Secondly, we would like to develop a new algorithm based on deep learning plus density ratio estimation. One such approach was proposed by Nam and Sugiyama in 2015, and we would like to build on that work. Density ratio estimation involves looking at the ratio between the probability distribution for the unknown data divided by the probability distribution for the known data. As a simple example, look at these two probability distributions that are in 2 dimensions between training and deployment phases. As you can see in these 2 plots, the red cluster and the blue cluster are fairly consistent in both training and deployment. However, in deployment, the green cluster and the purple cluster appear, and a density ratio-based approach would be able to identify them. Now, this project has a number of strategic connections, such as with the DARPA Ceylon project going on at OSU, and also the DARPA XAI project that OSU has a team for, and also the CU SafeML projects. In terms of deliverables, for year one, we would like to develop this new deep learning open set detection algorithm based on density ratio estimation. So we will deliver research papers and algorithms. We will also deliver software and tutorials for our industry members. In year 2, the goal is to extend this work to time series data, which is a much more challenging problem. As before, we will deliver research papers and algorithms, as well as software and tutorials. So in summary, our goal is to improve robustness of deployed ML applications to these unknown unknowns. The methods we will use are deep learning plus density ratio estimation for open set detection. The impacts are more robust classifiers in real-world settings, and we hope that we can improve user trust in deployed machine learning systems. For deliverables, we will deliver research papers, source code, implementations, and tutorials for industry. Finally, thank you, and I look forward to the discussion in the small breakout rooms.
All right, hi everyone. I'm Minsuk from Oregon State University. I'll be talking about my proposal on creating visual analytics tools for debugging AI or machine learning models. As you all know, state-of-the-art machine learning models have achieved significant performance at many tasks. However, these models still make incorrect predictions for many cases. Suppose there is a 97% accurate model, which means it makes mispredictions for only 3% of cases, which may be okay for some applications, but can be extremely dangerous for safety-critical applications, such as self-driving cars or medical diagnosis. Practitioners are aware of the importance of examining these failed cases to ensure their models work okay and improve their models. However, it is very challenging to analyze these failed cases, especially for very large data sets. So our research question is, how can we help these people effectively analyze a large number of failed cases, specifically analyzing when it fails and reasoning about why it fails? Our solution to this challenging problem is to create visual analytics tools. Visualization has been successfully assisting practitioners in interpreting complex machine learning models by effectively visualizing what's happening inside the models and how the models respond to data sets used for model training. And our research group has successful experience of developing such tools, such as the Activist tool deployed by Facebook, which is designed for data scientists at Facebook to interpret their deep learning models. Our long-term research goal for this project is to develop a systematic human-in-the-loop debugging workflow consisting of multiple steps so that we can save people's time and resources for building well-performing models. They can just follow these steps. Our short-term goal for the first year is to build visualization tools for analyzing failures integrated with failure-type inference methods. Let me tell you some details about our approach. First, we will develop visual analytics approaches that integrate XAI techniques to help people to know when AI fails at a conceptual level. For example, AI doesn't recognize brown cat images. With that, the next step is to develop methods to reason about why AI failed to recognize these brown cat images. So we'll be focusing on some common dataset related issues, such as insufficient data, dataset shifts, or labeling errors. For example, these brown cat images were not recognized because most cats in our dataset are black or white. The tool will give such guidance, and with that information, people can gain insights for what they can do next to fix this problem. For example, they may add more brown cat images to the training set. And this type of dataset-related issues are very common in practice. And in developing this tool, we are planning to conduct participatory design with industry to make sure our tool meets their needs and use cases. And we'll be leveraging our extensive experience of developing visualization tools for XAI tasks, including ones deployed by Facebook, a popular educational tool open source with Google, and several ongoing projects at OSU. So for the first year, we'll be developing a visualization tool. We'll also be conducting qualitative studies to investigate current practice of debugging so that we can incorporate some best practices into our tool. For the second year, we'll continue developing the tool that supports the entire debugging flow and evaluate the tools with some potential users from industry and letting them use our tool for their use. And we also plan to open source our tool. To sum up, we propose to create novel visual analytics tools for debugging machine learning, specifically for analyzing when model fails and why they fail. And it'll be based on our successful industry collaboration experience. And I look forward to working with our new partners, and I'll be happy to talk with you more about our project and your interests. Thank you very much.
Recent success of deep reinforcement learning in teaching computers to play video and board games with superhuman performance has sparked interest in the applications of reinforcement learning in programming safety-critical software systems. These novel software applications, such as autonomous vehicles and medical devices, demand rigorous guarantees on the correctness at an ever-increasing scale. My name is Ashutosh Trivedi, and I work in the area of developing formal methods to design and verify safety-critical software systems. I want to talk to you about my vision of improving usability, scalability, and trustworthiness of reinforcement learning in programming applications. Reinforcement learning is an optimization-based approach to problem solving where agents rely on scalar reward signals to discover optimal solutions. Recent advances in deep learning have propelled reinforcement learning as a leading human-AI collaborative programming paradigm in two exciting contexts. The first one is programming synthesis context, where a programmer provides a partial sketch of the program filled with holes, and reinforcement learning then completes these holes by repeatedly interacting with the environment. And in the adaptive software context, where the reinforcement learning is used to engineer software systems that use information about changes in the environments or requirements during its lifespan to modify their behavior. As a consequence, reinforcement learning algorithms increasingly operate with programmatic representations of the environment, the agent, and the reward signals. We dub this setting Programmatic Reinforcement Learning. Despite such powerful applications of programmatic reinforcement learning, the current state-of-the-art solutions suffer from several challenges hindering successful applications. I will touch upon some of them in this talk. The state-of-the-art reinforcement learning requires programmers to specify the requirements in the form of scalar reward signals. Often, non-experts provide these translations under significant time pressure. Such manual translations are time-consuming and error-prone. Software systems pose additional scalability challenges for reinforcement learning in the form of infinite state space due to numerical data types and potentially unbounded procedural call stacks. Current reinforcement learning approaches overcome this challenge by relying on programmers' expertise and insights in providing suitable approximation schemes. As the complexity of software grows, manual approximations get prohibitively expensive and lead to low productivity and low assurance. Moreover, the resulting lack of automation results in a significant barrier to entry in this promising field. To overcome these challenges, we propose a formal methods-centric approach to programmatic reinforcement learning. Formal methods are a highly successful approach to design safety-critical software systems that emphasizes on the use of rigorous specifications at every step of the design process. We aim to improve usability by enabling rigorous logical and programmatic specifications to express learning requirements instead of scalar rewards. We use these formal specifications to improve the scalability by automatically computing software abstractions guided by specifications to reduce the problem space. And finally, we focus on the trustworthiness of programmatic reinforcement learning by developing a formal verification framework by rigorously proving correctness guarantees about the designed system. Our long-term goal is to develop a formal abstraction-based approach to programmatic reinforcement learning built around the state-of-the-art formal reinforcement learning toolbox MongoJerry developed in my lab. MongoJerry translates formal logic-based learning requirements into scalar reward signals used in reinforcement learning. We plan to extend MongoJerry with programmatic inputs for the environment, agents, and the reward signals. We will develop a specification-guided software abstraction approach to tackle the infinite state space, and we will develop novel reinforcement learning algorithms to handle potentially recursive structures of programmatic reinforcement learning. We integrate a formal verification engine with this synthesis approach to provide rigorous guarantees about the learning outcomes. This is a 2-year project, and we will deliver the following tools and techniques. In the first year, we will develop a reinforcement learning-based program synthesis tool with a Python interface to complete simple or non-recursive partial programs under formal requirement specifications. We will also develop a domain-specific language to provide learning requirements in this setting. In the following year, we will develop and implement novel reinforcement learning algorithms to handle recursive structures in programmatic reinforcement learning and develop formal software verification approaches to provide guarantees about the learned outcomes. In summary, our goal is to improve the usability, scalability, and trustworthiness of programmatic reinforcement learning by developing a formal methods-centric approach. This project will extend the state-of-the-art formal reinforcement learning toolbox MongoJerry to integrate formal specifications with programmatic reinforcement learning. To scale this approach, we will create specification-guided abstractions, and we will develop formal verification support to verify safety of the synthesized programs. I welcome your questions and look forward to the discussion in the small groups.
Hello, my project is explaining and improving deep networks for vision and language tasks. As we all know, deep neural networks have achieved tremendous success in many tasks, but the question remains, can we trust them? Trust is important in all applications, but it's especially crucial for safety critical applications like autonomous driving or personalized news service. When the customer doesn't have trust, the application will not be deployed. And worse yet, if it is deployed, it will lead to some kind of disaster at some point. So it is important to build trust. In this particular project, we are exploring two different approaches. One is to build more faithful visualizations of neural networks than the current approaches. And the second is to understand the internals of deep neural networks. Both of these are expected to improve the neural network technology either through robust adversarial testing or by better learning algorithms and architectures. Suppose that we have a neural network and we classified this particular image as a race car. The question is why? Although the current state-of-the-art approaches do that explanation using a single attention map, it's often the case that a single attention map is not sufficient to describe the reasoning behind the neural network. In particular, in this case, there are at least 3 of these attention maps which give a very high score to classify this as a race car by a neural network. So in general, we would like to develop visualizations and representations that are more faithful to the original network. And secondly, we would like to explain the workings of neural language models by analyzing what information is represented at each layer. And thirdly, we would like to develop methods for robust adversarial testing of language models. Our current approach in computer vision consists of what we call structured attention graphs. These show a set of high-scoring attention maps and also how the scores change when some of the parts in the image are removed. So in general, we would like to implement new algorithms for generating these SAGs and other more transparent representations with high coverage. And in natural language processing tasks, we would like to use probing tasks to explain what each layer in the neural network is representing. And we would like to study human adversarial attacks of question answering systems to stress test the neural network, and also develop algorithms for automatically generating adversarial examples. So the deliverables for the first year include software for translating neural networks into transparent representations, which we call local explanations, and developing software for probing natural language processing models to generate global explanations. We would also like to present a tutorial on explainable machine learning at the end of the first year. In the second year, we would like to focus on interactive interfaces for adversarial testing and collect human-generated adversarial examples. We would also like to develop software for automatically generating adversarial examples and present a tutorial at the end of the second year on adversarial example generation. In summary, the goals of our research are twofold: deeper understanding of how neural networks work in language and vision tasks, and improving the performance of deep networks through robust training and design of better architectures. The methods include constructing equal and transparent representations, explaining language models through probing, and adversarial example generation and training. The deliverables include algorithms and code for generating structured explanations and adversarial examples, and also tutorials on explainable machine learning and adversarial example generation. Thank you, and I look forward to a discussion in the breakout room on our project.
This research is about improved accessibility and mobility using a topological approach. Accessibility and mobility need is constantly changing due to population growth and migration, as well as evacuation during natural disasters, such as the recent wildfires on the West Coast. Accessibility and mobility is greatly impacted by the location and capacity of resources such as hospitals and shelters, as well as the connectivity and the capacity of the road network. How do we improve the resilience against uncertainty in accessibility and mobility is the long-term goal of this research. Specifically, we'll look at how to accommodate our society's need for accessibility and mobility based on statistical prediction of short-term and long-term changes. For the first year, we will work closely with our industry partners to identify critical issues in route planning, resource placement, and emergency management, as well as develop topology-based analysis and visualization tools that allow data stakeholders to better understand their accessibility and mobility data. For the second year, we'll incorporate prediction models into our analysis and visualization framework and continue collaboration with our industry partners to deploy our software. Our approach is based on topology, a modern branch of mathematics that is concerned with the connectivity of spaces. For example, here, in a space with objects and roads, we can use topological singularities such as the green dots and the cyan dots to identify dead ends and T-junctions in the road network. Our fundamental approach is to use topology. More specifically, we'll look at network homology for accessibility and mobility analysis, tensor field singularities for path planning and resource placement, and bifurcations to model changing accessibility and mobility needs. We plan to leverage our past research in path planning using topology and procedural street network design. We're also currently in the last year of an NSF project on tensor field topology. We have collaborators in many international countries, such as University of Stuttgart, University of Leipzig, King Abdul University of Science and Technology, and University of Nottingham. For the first year, we plan to develop a tutorial on topological data analysis. We'll also develop analysis and visualization techniques for our partners' accessibility and mobility data. These techniques will be implemented in the form of software tools. We also plan to report our research in the form of research publications. For the second year, we'll incorporate prediction models of accessibility and mobility into our analysis and visualization framework and implement them. To summarize, our goal is to improve the resilience of our ability to address constantly changing accessibility and mobility needs. Our methods are based on topology, and we also plan to incorporate prediction modeling into our topology-driven approach. With our methods, we hope to help our industry partners and data stakeholders to better understand their data, which can, in the longer term, lead to increased resilience against short-term and long-term changes in accessibility and mobility needs. The deliverables include tutorial, software with source code, and research papers. Thank you for your attention. I look forward to answering your questions.
So the ways we currently envision data analysis are static. They remind us of long hours, sitting in front of monitors, hammering on keyboards and mice. However, as technology becomes more pervasive, decoupling data analysis from the places where data is collected and used severely limits our ability to use data effectively. I want to present a vision for the future of pervasive analytics that reunites data and action by physically moving data into the real world. When I use the term data analysis, you probably envision a scenario like this: large banks of monitors, and when complexity or scale become a problem, you just throw more pixels at the problem. However, this vision is not necessarily the reality of data. In many cases, data analysis occurs beyond the monitor. For example, we may have operators out in the field monitoring a bank of sensors on a mobile display, or you might have a hub somewhere in a smart city where people are working in an embedded display trying to gather information about anything from the state of transportation to critical information in a time of emergency or disaster. And when we've talked with experts who work in the field, be it emergency response or field science, about the challenges that traditional analytics play, what we see is two patterns: challenges of time and space. People need to be able to analyze their data when and where that data is collected in order to be able to act on their findings. We propose to remedy these issues by developing a suite of responsive visual analytics tools tailored to support exploratory insight and decision-making at the point of action. That is, the time and place that that data can be used. And the way that we will do this is by developing a novel toolkit that allows us to automatically retarget our visualizations and redesign visualizations to best suit the display that an analyst is working with. We will design these visualizations to optimize decision-making at the point of action, allowing people to quickly and accurately understand what's going on in their data, using a variety of interaction techniques tailored to the scenarios that they're working in. Our approach for creating this toolkit consists of 4 steps that will allow us to innovate, integrate, and enhance the ways that people are currently using data visualization. So first, we will build on our existing platforms to conduct a series of experiments that allow us to understand what makes data visualization effective at different scales and across different display types. We will then take the findings from those studies to construct a responsive visualization toolkit. This toolkit will allow us to automatically move visualizations from the desktop in the operations center to the mobile phone in the field to the display embedded in a hub or on a robot to HMDs in physically taxing and tolling environments. And it will allow us to do so without loss of information. After we've done this retargeting, we will explore the ways that we can help people interact with and explore that data by integrating an expanded natural language query system into the toolkit, allowing people to use spoken voice and natural expression to try and explore and navigate and refine their data in real time. Then finally, we will develop an active learning-based intelligent agent that allows people to work with their data at scale and be able to start to navigate and collaboratively adapt to different scenarios or different analyst inputs based on the information that's provided to the system. This agent-based system will allow us to scale people's abilities to navigate large data corpora quickly and efficiently. The deliverables coming out of this project will be twofold. In year 1, we will create this responsive toolkit and integrate display-based visualizations and a technique for automatically adapting and selecting visualizations based on the parameters of the display. We'll also integrate a preliminary natural language interaction. In year 2, we will work with partners to expand this natural language query system to the needs of specific scenarios and construct this adaptive intelligent agent, including interactive explanatory dashboards. In summary, this work will create a visual analytics suite for integrating analysis back into the field and supporting data-driven decision-making at the point of action. I look forward to the discussion.
This is the end of the broadcasting from the main stage. It's time for us to go now into the sessions tab in Hopin, where we're going to go into the Ask Me Anything session and get a chance to ask questions for the presenters. Shiv, thank you so much for being my co-host and co-director.
Thank you. This was wonderful. See you in the sessions now.